In this video we'll be taking a look at the DMA system in our Z80 computer project. I haven't actually tested it so far other than checking to see if the counters can be loaded, but I'll come back to that in a few minutes. So I wanted to video the testing for two reasons. One is so that you get to see it, including all the issues that we're most likely going to encounter, but also it's a good record for me to have so I can see what testing I've done, what the results were, without having to try and remember it all. So just to start off with, we'll just recap on what the DMA is for and why it's an advantage. Now, the previous testing I've done and shown on the videos, and the testing I've done so far with this setup, is what's called programmed in-out. So that entails using the Z80 and to write bytes one at a time to the disk or the disk controller, and read bytes one at a time from the disk controller. The problem with that is it's very code intensive, it's very processor intensive. In fact, it's so intensive that the board cannot keep up with double density rates at 2.5 megahertz. So for that to work, it has to be set to 5 megahertz. Not really a problem, but even then it utilizes pretty much 100% of the processor time. And even then it only just keeps up. In double density mode, which is the disk format I'm currently using, there's a byte required to be written to the controller or read from the controller every 32 microseconds, and that's not many instructions with the Z80. Now if you go back and look at some of the previous videos, I showed the data or the raw data coming out of the drive. And what you will have noticed is there was appreciable, we'll call it jitter, on the timing of the reading and writing of the bytes to and from the floppy drive controller. And the reason for that is the Z80 was responding to the floppy drive controller, setting the DRQ line to inform the Z80 it was ready for the byte to be written or read. But depending on where the Z80 was in its code loop, it might take a couple of instructions before the Z80 responded. And so if it was one instruction or two instructions, it can make a 4 or 5 microsecond difference in the time before the DRQ line was then reset. And that's why we saw jitter. With the DMA that shouldn't occur. It should be very precise timing, but also it should take up far less of the processor resources. So if we look back at the diagram I showed previously of what DMA is, and I've had some comments saying it's not DMA, it is DMA, it's direct memory access. It's where the device accesses the RAM directly. It directly reads data from the RAM into the floppy drive, or vice versa. So direct memory access, that's really what the definition for it is. And this is really how it works. So during a transfer, the Z80 is not really involved. The Z80 releases the address bus, releases the data bus, and releases some of the control signals such as memory request, read and write, that sort of thing. And then our circuit takes control of those, and it uses those in the same way the Z80 does to read or write data. And then it transfers that data into or out of the floppy drive interface system. So this is what we're trying to achieve. So the way our circuit gains control of the data bus, address bus and control lines is by asserting the bus request line, and that does not give it immediate access. It's really, as it may be apparent by the name of the control line, it's a request to the Z80 for permission to use those lines. And as you can see in the timing diagram, this is from the Z80 handbook or user manual, and the bus request is driven low by the requesting device, and then at the end of the current machine cycle, the Z80 should grant the bus acknowledge, and at the same time it will release or put into tri-state the address bus, the data bus, and these control lines, and they all then go into tri-state mode. Now at that point, of course, our system can make use of them, and if our system's connected to the address and data bus, for example, and the control lines, it can read to read from RAM and write to RAM in the same way that the Z80 can. And rather than duplicating all the memory decoding, etc., we can make use of exactly the same memory decoding and all the control systems and the RAM, the DRAM, everything else, as long as we stick to the same sequence of clock cycles and events that the Z80 itself uses. So if we, for example, want to do a write, then we would go through a standard Z80 write cycle. If we want to do a read, we'd go through a read cycle. Now this is quite a complex system to implement, and someone asked me what memory controller I was using for it, and the answer is I'm not. This is again all discrete. It's discrete logic, and there is no DMA controller other than our discrete circuits. Now I have shown the breadboard version of these. You've got the floppy drive interface itself, which I've shown previously. That's the board or the breadboard that was attached to the version 4 processor that we looked at in previous videos. We then have a 16-bit counter, and that's over in this area. The counter has to be loadable, so we have to be able to load that so we can tell the system what address we want to read from or write to, and then it counts as each byte is read or written and keeps track of where the next one should go. But it also needs some isolation buffers so that it's not trying to put data onto the address bus when we're not in our bus acknowledge phase of the system's cycles. Otherwise the system will just crash. So we also need to be able to load it with a 16-bit value, 8-bit data bus of course, so we have to load it into discrete steps. So this is the first part I tested. I won't show the testing of this, it's fairly tedious, but we have the 4 counters down here. So the 16-bit counter is made up of 4 cascaded 4-bit counters, and these are 74161s, arranged as a 16-bit loadable counter. And one of the complications with the 161 is that when you assert the load pin on these devices to load them and apply the data input that you want, that's 4 bits of data to each one that you want to load into it, that data won't be loaded until you supply a clock pulse to the clock input pin, because they're synchronous load. So that's a complication we have to deal with and add to our discrete logic, but also the same clock pin needs to be available to the DMA control system because it needs to increment the counter as part of the DMA transfer process. So it's a relatively complex counter circuit, but I tested this by trying to load it with different values and then looking at the output pins using the scope, and it seems to be doing exactly what it should. The way it's accessed is similar to the way we access the floppy drive controller internal registers using our programmed in-out system, in that it's accessed through an in-out port. And in fact all the control for the floppy drive interface and the DMA interface are controlled through port 5, either input or output through port 5, and then there's further decoding to determine what address within port 5, if you like, we're trying to access. And that works quite well. It means we only occupy one of our 8 ports that we've decoded on the board, and that's for the entire DMA and floppy drive control system, including the counter. So 2 of those port addresses are effectively used to load the address counter, and that seemed to work. So all I was doing to test it was using our monitor program, using the out command to send values to the correct address and correct port, and they loaded the correct value. So that's as far as I've got with the testing. I have fully tested the floppy drive, of course, but the general circuit, I'll show you the actual circuits later. And one of the reasons, by the way, I don't show the circuits as we go along is I get a lot of let's call them helpful comments, but I don't think a lot of people realise I'm showing a work in progress, so they're asking why I haven't done this, why I haven't done that. And the answer is, well, it's not finished yet, so just wait until the end if you want to criticise it for not having a particular feature. but I go through a design process and that's what I'm showing. And also quite often the features they're talking about are already there. I just haven't shown them because it's not really been pertinent to what I was trying to explain. Okay, so the general layout for the DMA control system is this. Probably looks a bit complicated, and it kind of is. It's fairly easy to implement in theory, but the detail can cause issues because it has to work seamlessly with the Z80 and the rest of the board and the floppy drive control system. Otherwise, most likely the machine will just crash and could even end up with damaged devices. So all we have is the counter at the top. This is the 16-bit counter I was just showing, and the buffer, as I said, is used so that we can only put the address value from the counter onto the Z80 address bus when we're in the bus acknowledge phase of operation. And so this buffer is controlled from our DMA control logic. The PIO is programmed in out because, as I said, I wanted the system to be able to use programmed in out or DMA, and that's how in theory it should work. Programmed in out is working, I've shown that, but in this video we're looking at the DMA mode of operation. So we've got a counter that counts the address that we're trying to access in RAM, and we load that before we start the process. So the general usage of this is we load the address we want to use, we program the floppy drive controller using, again, in-out Z80 commands or instructions to load the value, and then we start the thing running in DMA mode, and in theory it should transfer without further demands on the Z80. We've got then a data buffer. Now this is where things started getting complicated because the data buffer needs to work in both directions. It's a bidirectional buffer and it needs to operate in the correct direction, but it also buffers other circuits as well. So we need to make sure it only switches on or transfers data onto the data bus when it's supposed to. Otherwise, again, we'll most likely crash the Z80 system itself. And again, that is controlled through our control logic. We've then got a latch which is used to determine the mode and whether we enable DMA or not, the direction, whether we're reading or writing, and a few other things as well. This is simplified, but the control latch determines the general operation. And again, we load that through port 5 in-out as part of the configuration for our DMA. And that actually controls the control logic for our DMA system. To enable all this to work so we can access it through the port, we need some port decoding. So the board already has decoding to decode for port 5, but we then need to further decode the address bus in order to determine which address within the port we want to access, and that then further allows us to control the operation of our DMA system. We have another buffer down here that's used to isolate the output lines from the DMA, which go through to our memory request, write, read, in-out request lines, and that's so that we're not trying to drive these when we're not in our bus acknowledge mode. Otherwise, once again, the Z80 would crash. And finally at the bottom here we've got the bus request output, which goes to the Z80 requesting permission to use the bus, and then we wait until the bus acknowledge signal is returned from the Z80, and then we go into our DMA mode. And remember that we're only transferring 1 byte at a time here in each DMA cycle. So for each bus request that we issue from our DMA circuit, we get a bus acknowledge and we transfer 1 byte of data, we hand back control to the Z80, and then we wait until the next byte is either required or available with our floppy drive interface. We'll see the advantage of this in terms of timing in a few minutes. We'll look at that process using the scope. But just bear in mind that using programmed in-out, we utilize 100% of the processor cycle time. Now the control logic then interfaces with our floppy drive interface, and then we have, or rather floppy drive controller. The floppy drive interface itself I haven't shown. That's what was on the board that was attached to the version 4 board that we saw previously. So we have the clock coming in. That's the clock that drives the Z80. It's divided down, goes to our floppy drive control system. It actually also controls the DMA control logic as well, because we need to synchronize this, of course, with the Z80. So this control logic, it's relatively complex, and this is what I showed on this breadboard. So this is our DMA control logic, and as ever I've kept the circuit as simple as possible. You could over-engineer, over-design this, end up with a very complex system. What I do, generally speaking, is I design it in the CAD system, and then I go through it in terms of just thinking how it works. Someone I used to work with called it Imagineering. It's not a term I particularly like, but it does get the point across, where I'm kind of going through the operation without physically making the board up. Then I do the breadboard version, make sure it works, simplify it further if I can, and then I put this onto the main board. Now, having said that, I'm not really expecting this to work, which is why I wanted to video it. It's a very complex thing to implement, so it'd be interesting to see exactly what it does. Now, in terms of the output and termination of the DMA cycle, the floppy drive controller outputs an interrupt line when the operation is complete. In this board, I've designed it so that that bit is available in our global status register, and it also can generate an interrupt, a hardware interrupt, if that interrupt is enabled. Remember that the interrupts on here use Z80 mode 2 hardware interrupts, which use hardware vectoring. So you can drive the DMA through an interrupt system if you want to. That's not what I'm doing for the testing. I'm actually polling the global status register. But as I say, you can use interrupt if you prefer, and that's kind of useful if you're using or writing a multitasking system, because it means you can read and write floppy disks using very little Z80 resource. Okay, so this is what we're trying to implement, and that's what's on the board. So the next thing we need to do is to see what happens when we try to run this. So I haven't tried this yet. I know the board boots up, so it's booted up now, as you can see, but I haven't tried actually running the DMA system. It needed different software. Now, this is not the software in the boot ROM. The boot ROM is identical to the one that we used in the version 4 board. In fact, it's the same ROM. I just took it out of the version 4 board and put it into this one, so that didn't need modifying. But I had to write new code, test code, to send through the RS-232, and that's what we'll do now. So we'll start by putting a floppy disk into our drive. Now, I have changed the code that I used previously, so this is the same code I had before for the programmed in out. All I've done is modify it, so in theory it should enable the DMA, and you should see the blue DMA, that's the one closest to us, come on, and we should then be able to read the disk. Now, I've only so far modified it to use DMA in read mode. But we'll see what happens. It should in theory do the same thing. I'll show you the code that I've written for this before we get started. So it's very simple. It goes through it. It loads the floppy drive controller in the same way it did previously, but this is where it gets different. It then loads the DMA counter. So that's the counter we looked at a few minutes ago, and it loads a value here of F880. So that's the start of the second line on the video RAM. So in theory it should write the data, and it should write it into video RAM, in which case it should appear on the screen. You would normally of course use a memory buffer somewhere else so it doesn't send the data to the screen, but this is just a shortcut way of seeing if it's working. It then goes through, carries out exactly the same steps it did before. Remember, this part is configuring the floppy drive controller chip, which does not yet involve the DMA. So we've loaded the address we want to send the data to. We then decide which side of the disk we're trying to use, and so it sets a bit in the command that we're going to send accordingly. There's a value stored in RAM saying which side we should be using. So once it's done all that, it's ready to start the process. So this is where the floppy drive controller is basically told to start reading. So it sends that command, including the side, to the floppy drive controller. The floppy drive controller should then start trying to read the floppy disk. Once it's got the first byte, that's when our DMA circuits kick in. The DRQ output, if it's in DMA mode, the DRQ output is used to tell the system to generate a bus request, and if that then it waits for the bus acknowledge, and it then starts a write cycle to RAM, where the source for the code is the data register within the floppy drive controller, and the destination is the current address pointed to by our DMA counter. Okay, so once this starts, our Z80 needs to do nothing more other than wait for the read to finish. So that's not waiting for the byte to be read, it's waiting for the sector read to finish, because we're issuing a read sector command, so it's going to read the entire sector. Incidentally, I was asked why, if we only have 32 microseconds, I pointed out in a previous video that we're limited on time as to how long we've got between each byte read, and someone asked why we don't just use skew to avoid that, because you can introduce skew into floppy disks. Well, you can, but that's skew between sectors. It's not skew between bytes within a sector. So once you start reading a sector, generally you read the entire sector, and you can't introduce skew while you're doing that. You need to allow the entire sector to be read, and you have to do that in a timely fashion. The idea of skew is that once you read a particular sector, if you then start to immediately read the next sector on the disk, because it's running continuously of course, your system won't have time to handle the data you've read from the previous sector before the next one is being put into RAM. So if you skip a couple of sectors, then that gives more time for the system to deal with the data, and then it's immediately ready to read the next sector, and you just kind of effectively leapfrog sectors until you've read the entire track. But it allows you to run at a much faster throughput rate in effect, because you're not waiting for the next sector to come right round a full revolution. The order that you generally do that and the number of sectors you skip is entirely up to you, and you can actually change that in systems like CPM. There's a table for looking that information up within CPM. I'm not using notes, I'm just reading them sequentially, but in this case we're only reading a single sector. But we can't use skew to slow things down, because that only applies to entire sectors. Okay, so as I was saying, once we start this process, the Z80 will now just sit and wait for the process to end. It could go away and do something else between each byte being read, or this bottom part of the code could be in an interrupt handler, and then the system can just be running other software while the disk process is underway. But once, in this case, we sit and wait for the process to end, holding the status register, and this is the global status register in our Z80 board, not the status register in the floppy drive controller. Once it's finished, it just homes the drive, waits for a short time, initializes the latch, that's the control latch for our DMA, in which case it just deselects everything, and then it just terminates. There's a delay down here just so we can see what it's read before it does anything else. Okay, so we'll load the code that we need into the Z80. So we'll type in the correct address. I'll just go and send that from the PC. Okay, so the program has downloaded. It's an unformatted disk, so the first thing we'll do is try and format the disk. The format command still uses programmed in out, so and this is not going to, at least in theory, it should not use DMA. So we'll try formatting. So I'll speed things up for this part. Okay, so the format's finished, and what we'll try and do now is read the disk. So I'm not quite sure what's going to happen. I kind of suspect the Z80 will crash. As I say, it's quite a complex thing to implement, especially as all the buffering was changed. But in theory, what we should see is the DMA LED should come on, and in theory it should read the sector. But as I say, I suspect something else may happen. But we'll give this a go and see what the result is. Forgot to actually hit the command key there. Okay, I'm just going to go and reload the software. Okay, I've reloaded the software. We'll try that again. Okay, the reason I reloaded the software is I wasn't sure if I'd loaded the correct software. I wasn't really expecting this to work quite as well as it has. It has loaded the software as it should do. The only reason it's showing a rogue character up here is that's the cursor reappearing after it's written. Okay, what I'm going to do is try monitoring the bus request line. So I'm a bit suspicious that we're not actually using DMA. I'd be a bit surprised if we got this working first time. So we'll try doing that again, and we should, if it's using DMA, we should see each of the requests. Didn't see anything. We'll try and do a single caption and see if we can see anything. Trying to work around the camera here, so it's a bit of a stretch, but okay, well clearly it's doing something, and we should be getting. Okay, well the scope's set to 10 microseconds per division, and we should be seeing one of these pulses every 32 microseconds. As you can see, we are. So it does appear that it's actually working. What we'll do is we'll look at the bus acknowledge line and see if the Z80 is actually issuing a bus acknowledge. Okay, so we'll try that again. Which it is. Okay, that again should be 32 microseconds per byte, which it is. Should be 256 pulses, but I'm not going to count them. Okay, that's again a surprise. I wasn't really expecting to get this far. What I'm going to do now is go and modify the write code, so we can try writing a sector to disk and see if that works as well. And that will of course use the write part of the circuit. So I'll go away and do that. It'll only take a few minutes, but it'll just be a few seconds for you. Okay, I've modified the code, so now it should use DMA in write mode. And if we just examine what's in memory, I've downloaded the code, haven't tried running it yet, but if we look at this address, this is the data that should be written to the disk, and to make sure we're using the DMA version and not the version we had before. These three letters where it says DMA, in the previous software it said FDC, so we'll know if we're writing the correct data. So what the code does, I have printed it off, so we'll have a quick look. It's almost identical at the start to the read sector. Now the only difference is it's loading the write command, of course. But it loads the address of the data we want to send to the disk. Now in this case this is at A500. This is of course produced when we load the software in through the RS-232. So of course we load A500 into the DMA counter to make sure it gets this data from RAM. It then goes through, initializes and prepares the floppy drive controller, and then it does exactly the same thing as before. It sends the command to the floppy drive controller. In this case it's a write sector command, and then we just wait for that to finish. Now once again we could go away and the Z80 could do something else. And in fact, if we look on the scope, notice that we're using 1 microsecond of processor time every 32 microseconds. So we're only using about 3% of the resources or cycle time of the Z80, as opposed to 100% when we're using programmed in-out. So very efficient way, and that's the advantage of using DMA. A lot of trouble to go to design it, but well worth the time. Okay, so we sit and wait for this to finish, and in theory the DMA should get the data from RAM, and this is where it's located. It's just told to be at A500, and that's why we load the DMA address counter with that value. It should read these bytes one at a time on each DMA cycle, and for each bus acknowledge cycle it should transfer 1 byte and then increment the counter, and then on the next cycle it should transfer the next one, etc. And then for each cycle it should write that value to the disk. So once again, not quite sure what's going to happen here, and we'll give it a go and see if we can successfully write the data. Now before we start, we'll read. It's a formatted disk. This is still the same disk we used a few minutes ago, so we'll reread it and make sure that that function still works, and also what data is at this particular part of the disk. And as you can see, if you recall, that's just the data value that is used when we format the disk, so it just appears that way for that character on the screen. But what we should see after we've written the data is whatever data we've put into the buffer. So we should write this data, and after we've written this, when we read the same sector back, this is 1 full sector's worth of data. When we read that sector back after writing it, we should of course see this. So we'll try the write function. Now once again, don't be surprised if this doesn't work. Okay, well it hasn't crashed. I'm just checking the current draw, by the way, on the power supply. One of the dangers here is if I've made a mistake in the circuit, it could result in more than one buffer trying to put data onto the same bus at the same time, and of course that's not good. But the current looks fine, so I don't think that's happening. But we'll try and read the sector back. Just because it's obviously finished doesn't mean it's actually done anything. So we'll try and read that back and see what happens. Okay, well it's actually written that data successfully to disk, and it is saying DMA, so we know it's the new code. We'll try it again on a different sector, so I'll try modifying the values in RAM. So if you remember, we can change certain values in RAM. So 05 is the sector number, so we'll change that to 07. 08 is the track number, so we'll change that to 12. That's a side, but we'll jump out of that. And we'll try reading this. It should just be the format data again, because we haven't written to this sector yet. Which it is. We'll try writing that, and it should be the same data that we used previously. And we'll try reading that back. And it's working. Okay, well, I was expecting this video to be a bit longer, or maybe the start of a series of videos trying to get the DMA to work, but it does appear to be working, and it seems to be working quite well. We'll just try rereading the same address again, make sure it does the same thing each time. Okay. Well, that's very good news. It means that the DMA system seems to be doing exactly what it's supposed to. I am going to be going through and doing a lot more testing on this, of course, just to make sure that it's doing what it's supposed to. It's all addresses and all both banks, and that it can successfully transfer data. And as I say, things are looking quite promising. It's certainly working a lot better than I expected it to the first time we've tried it. Okay, well that's it for this video. As I say, not quite as exciting as I'd assumed it would be. That's good for me, probably not quite so good for you. But that's probably the last video we'll see on this for a few weeks. I've got some repairs I need to carry out that have been sitting waiting for quite a long time. I need to get onto those, and I will video some of them. When we get back to this in a little while, the next step really, assuming all the testing goes okay for the DMA, is to start trying to implement a version of CPM on this and see if we can get that to boot up from floppy disk. But things are looking promising. It's much easier to implement CPM with DMA because CPM is kind of geared towards using it. You can use programmed in out, it'd just be a lot easier with DMA.